Hi, in this video we are going to discuss the concept of power, and we're going to define it and show how it relates to work and energy in mechanical systems. So let's start off by defining power. Power is the rate at which work is done by a force. And so in this definition, the important part of this is the idea of rate, and rate is going to tell us something about how fast something happens. So when we talk about power, the rate is going to be how fast is work being done. And so one formula for power would be to simply say power is equal to work done over time. And so that idea of dividing by time is important because that's where the rate comes from. Power is measured in different units. The units that we're going to use in class are watts. And 1 watt is equal to 1 joule, as in 1 joule of work for every 1 second. So a watt is equal to, excuse me, a watt is equal to 1 joule per second. Okay. There's another way that you can think about power that might be helpful too in some problems. Sometimes instead of talking about the work done by a force, you talk about the rate at which energy is transformed. And that's kind of going to be the same thing in many ways. The rate at which energy is transformed. And so you can also think sometimes about power as being some transformation of energy over time. And you'll see from the examples that we do that one, either way of thinking about power is kind of equivalent. The important thing is that power is a rate. Okay. So let's do an example here. Let's talk about an example involving average power. Okay. And so you could talk about an example like this. What if a force does a certain amount of work in, let's say that it does, for example, 500 joules. And let's say that it does that work in maybe 5 seconds. So maybe this is a machine that is lifting up a load of some kind, and it does 500 joules of work in 5 seconds. The power that is used by that force in this case would simply be 500 joules over 5 seconds, which is, of course, is equal to 100 watts. And so watts are written like that. Okay? Let's take this same example, and let's say that we have information that is given to us in graphical form. So let's say that we have a graph of power versus time. And let's make the assumption here that our force basically acts with a constant power of 100 watts. It's always doing work at a rate of 100 joules per second. So if we were to graph that, it would look something like this. Okay? Again, this means that you have constant rate of doing work. All right, that's what that graph means. Now, the question would be, if you can graph that, and you look at this graph versus time, would there be a way to determine how much work is done? So find the work using that graph. Okay. And so what I would encourage you to do is to say, well, what does that mean to find the work? Algebraically, we would say that if you take the formula, you would say work must be equal to power multiplied by time. Okay, so just rearranging the formula would give us this. So in this particular case, you would have 100 watts times 5 seconds, and of course that's 500 joules. Okay. Alternatively, you can look at the graph and you can say, well, let's look at this graph and let's look at the area under the graph. And the area under the graph, in this case, would just be the area of a rectangle, which is 100 watts tall by 5 seconds wide. And of course, that's giving us the same answer of 100 times 5, or 500 joules. And so I wanted to just show you this example because if you have a graph of power versus time, the area of P versus T equals the work. And that's an important thing for you to know when you solve power problems. Okay. One last example that's similar to that would be, what if the power changes? So what if you have power versus time, and the power changes, like so, where it takes you a while to develop a power of 100 watts. So at the very beginning, at 0 seconds, the power is 0, and then time goes by. And when you get to 5 seconds, the power is now 100 watts. Okay? The question would be, how much work is done? Okay? Now, if you want to do this algebraically, you can. You just have to be careful. Work is equal to power times time, but you would want to use the average power in this case. So you would have to put average here, because this power is changing. And so my average power in this case is 50 watts, right? Because 50 is kind of right here on the graph. And so if I take 50 watts times 5 seconds, you can see I'm doing 250 joules of work. Okay? Notice that that's half as much work as I did before, because my power takes 5 seconds to get up to 100 watts. Okay. And finally, what you can also see from something like this is, what if you just take the area under this graph? We should get the same answer, except now you have a triangle, and so the area is equal to 1/2 base times height, so it's 1/2 times 5 times the height of 100, and of course that's also 250 joules, and so we get the same result again. So the bottom line is that if you have any graph of power versus time, you can always take the area underneath to find the work that's done by the force, and that's just a general rule. From a calculus point of view, what we're saying is that power can be written as a derivative, right? Instead of saying power is work over time, you can replace work and time with dW and dt, okay? And then you can basically distribute the dt over by multiplying it, and and you can integrate both sides. And so when you take the integral, this is really the area of a PT graph. And that's equal to W total. So we'll do some examples of that, but basically you're finding the area of a graph or you're taking the integral, it's the same thing.